Wat is je jointstip?
We hebben niet aangepast, dus niet aangepast. Nee,
Yeah, welcome class to the third lecture on multibody dynamics. I hope everybody read the announcement. Let me check if all systems are go. Yeah, looks like it. Stop. Yeah. I hope everybody read the announcement about the scoring algorithm and the feedback score. It turned out that I made a mistake. I didn't check my work. When we had a MATLAB course, it used the scoring algorithm to determine what your feedback score is. Between the MATLAB course and this course, they changed the scoring algorithm. So suddenly, some people got no feedback score, although they gave feedback. Luckily, we discovered that, and it's all turned back, so everybody should be in the clear now. Everybody should have a feedback score when they gave feedback. And if there's something missing, then please talk to the TAs. And I hope everything will work out then. The other issue was about the PDF viewer in peer grade. It shows a glitch. In some cases, pages are blank. So my strong advice is always when you do review, first download the thing you have to review. Do it in your own, view it in your own viewer, and that then should work.
I tried it as well, but that didn't work out.
Then there's something wrong with the PDF. Yeah, or your viewer, but that's hard to imagine. So it probably is something really wrong with the PDF. Yep. And just write to the TAs. Yep. Okay. What are we going to do today? Kahoot, eh? Yeah. Let's start with Kahoot. So, Kahoot. Okay, Kahoot. Where is Kahoot? Here you are. In-class quiz 3. Play. Let's make it full screen. We are classic, right? Yeah. Okido. Oh, start, sorry, yeah. Stupid. Oh, no, not start. Do. Kahoot is becoming more and more popular. I was at a project meeting some weeks ago, and one of the presenters in his 15-minute presentation used Kahoot to get the attention of the audience. So it's used on a very wide platform, from middle school until even project meetings. Okay, well. What is it? Okay. Seems like I have to scroll through the stuff. Oh, looks okay. Yeah, I can do that, no problem. I can do that.
Yeah.
Okay, let's start. Rotation matrices are still a problem, and they are in advanced dynamics, so it should be basic knowledge. Okay, it's super quiet in the room. I expect discussion.
Ik denk geel. Maar dan is het waar het geel. Ik denk. Nee, sorry. Nee, sorry. Groen. Nee, maar hij. Ik was gewoon niet.
X is rechter. Ja. Maar je roteert zo, want dat wordt allemaal plus, behalve de reden.
Ja, bij scoort ja, en het is negatief. Ja. Ik denk dat.
So when I look at the results, the majority says it's a rotation about the x-axis. I agree, because if you look at the matrix, then that's like the invariant, right? The x is not changing, and there's no contribution of x to the other components. So that is a good choice, either this one or this one. And then it's plus or minus. That is tricky. That is. First of all, you have to realize, is it from the body fixed to the space fixed, or vice versa? Because then it's minus maybe, if you go from left to right or from right to left. But it turns out to be plus, because, well, this is the giveaway actually. Anyway, those who in this field check with back or forth rotation. Okay, next is 8.5 in the room. No. Easy, eh?
Maar ik denk dat het maakt even twee manieren van ja,
Ja. Okay. Some people still think one, but it's two, of course. I mean, 533 in the room. You have 120 seconds, so take your time. Scribble on paper.
denk groen. Ja, maar ook plus I. Ook de min I plus I.
It's still very quiet in the room.
Reactie van nee, daarin. Wat is het min x en plus I? Sorry, ja, plus I. Ja, daarom denk ik dat hier. Nee, ja, ik wil die af. Ik had het een keer, toen deed je van laatste wedstrijd, toen deed hij het niet. Toen was het time.
Livestream answer.
Oh. Dat zou op zich best wel een grappig in deze.
We hebben zeer wat nee, ik dacht de oude. Ja.
Okay, when I look at the results, I see that 107 out of 146 are in the wrong, and I was afraid a little bit that this would happen. In your homework assignment 2, I specifically wrote interpret the Lagrange multiplier. So you have to look at what are they, what is the magnitude, what is the sign. And in the book there is a whole example on how can you interpret the Lagrange multiplier. There's a whole example. It's called 12.8. So it really helps if you read the book. I mean, it's just part of the material. So what is the problem here? When you add this constraint, well, everybody knows, of course, that the Jacobian of the constraint times the Lagrange multiplier are the forces on the system. So if you look at the Jacobian of the thing with respect to A, you get minus A, and if you take the Jacobian of the constraint with respect to Y, you get 1. So apparently those coefficients times the Lagrange multiplier are the forces which work on the system. So we go back to the answer. Of course, I threw in a number of answers, but apparently there are, we have to look at the constraint. So with X it should be minus A, and with Y it should be 1. And there we see. And it's minus. Well, anyway, brush up your stuff, read, what is it? Example 12.8. Jikke, where are you? Good work. Well, this is so easy, I mean. Or not, I don't know. So this is mainly about how does index notation with Einstein's summation convention works.
Okay. Wie zou er nou doen?
Nee, ja, dit van wit. Niet weer normaal, maar de het is allemaal goed en dan een fietsje waar ik helemaal klaar ben, maar het komt nog moeilijk terug.
goed gedaan, daar ook gedaan. Dus twee mensen boven daar. Iedereen heeft dan
Twee fietsen.
squat goal. Oh, zo'n squat.
Ja.
Twee antwoorden. Ja.
So, most of you were. So most of you were correct. Some were surprised that they see two correct answers, and being the blue one and what is this? Yellow or green? What is it? Yellow. Okay. The blue and the yellow one. Most people go for this, but remember with the index notation, the order doesn't really matter, and the mass matrix is symmetric, so you can do this summation. That's no problem. You can write this Vj in front here and the Vi there. It doesn't matter. It sums up like this. Okay. Yeah, Jikke, keep up the good work. That's the topic of today. Energy loss, or impact, among other things, but take your time, you have 90 seconds. You could also take the book. Those who have the book, take the book, look it up. Google it. Or ask Jikke. In the book.
Maar er is ook een eenheidswijze blok die blok is makkelijk hier snijden, die heeft een dan heb je ook niet energie, dan heb je vaak een factor een half erbij en er moet 1 min zijn. Er moet 1 min 1 zijn en verder scheelt het alleen maar een factor een half en dan moet je beginnen met 100% kinetische energie en een deel daarvan wordt afgevraagd.
So even without looking it up in the book or asking Jikke, for instance, or looking at last year's quiz, you could come to the right answer already on a dimensional analysis, right? I heard some voices here. Well, kinetic energy is mass times velocity squared. So if you have a velocity squared and no mass here, then you say, well, that can't be correct, right? Then P was the impulse. Likewise here, impulse is something mass times velocity, and if you square it, you get the square of mass. That doesn't work. So it has to be something with the impulse times the velocity. And then, why is this the answer and not that the answer? Yeah, why 1/2 and why not a 1? Well, it's all in the book. Okay, let's see who's the top scorer. Jikke. Wow, very good. I have to save the feedback. Please give me feedback. I give you feedback, you give me feedback. Sounds like say Kip. Okay. Then we're done here, right? Code go away, then up. I got to this one. Let me check if everything is still running here. Stop recording. Yeah, looks good. Okay, let's go to the content of today. Yeah, if we read the title, let me put the screen a little bit up. Yeah. If we read the title, I say systematic approach, continued, adding passive and active elements and doing impact equations. So first let's start with adding passive and active elements. Now what do I mean with passive and active? For instance, a passive element could be something like a spring, right? That's a thing you can apply forces to it, and it's also a way to put to store energy. And an active element, what am I thinking of then? Well, let's say you want to power the system, you need a motor or something like that. For instance, you have a thing like this, and here you put a current in the stuff. You have those two wires, and apparently here you get some torque and some output speed. That's an active element. We put electricity in it and you get mechanical power out of it. Okay, so those are the elements I'm thinking of, because until now the system has been very boring, right? It's just sticks and hinges, it's just joints and rigid bodies. We want to make a system out of that. Let's focus the goal for today is to find a systematic approach to add those passive and active elements to our equation of motion. And let's do it by example. So I want to start with an example. And the example is that I take our double pendulum thing and then I just add a passive element. So let's draw it in a bit of a simple configuration. So the thing is horizontal. Here's the center of mass. This is body 1, and then attached to that is body 2, but for now there's more, maybe even more. I'm not so interested in that. And then I'm going to attach a spring, and of course not at the center of mass here, somewhere on the body, for instance here. And to make it not too difficult, I'm going to attach a spring to the fixed ground, so put it somewhere here. It's not essential, but it makes, for now it makes it a bit simpler. So we have a spring here. Spring is not broken, yeah. Then we have to give names to the points. So this is A, oh yeah, we need a coordinate system, thank you. X, Y, rotation angle is like this, phi. This is body 1. Then we have a spring, and let's make our life simple. So we say it has some linear stiffness and it has an initial unstretched length which is equal to L, where L was the length of these elements. Yeah, this is this fixed point, and where is this fixed point E? Well, I choose as a height here L over 2. All nice simple numbers. And where is it attached on the body? So this distance is 2/3 L. So this, yeah. Okay. Now, what does a spring do? And especially in the case of a linear spring, you could say, well, if you have that spring, and if it's at its rest length, is L0, there is no force. So if I would draw a diagram here with the force of the spring, then that's 0. And the moment I'm going to elongate it, make it longer, something like this. So this is then this delta L. Then what happens, then I get a force, like that. And how big is this force here? Well, it has to do with the stiffness of the spring, right? So force here is equal to this constant K times this delta L. So just a linear behavior of the spring. Twice the elongation, twice the force. What is delta L? Delta L is the actual length minus the initial length. Yeah, and then let me repeat again, this spring law is then something like this, K times delta L. Now, how would you incorporate such a passive element to your system? There are, of course, various ways. One approach would be to cut this spring, or to calculate what is the length, minus the rest length, then you get the elongation times the stiffness, then you get a force. Then from the geometry you see what the direction of the force is, and then you decompose it in a y component and an x component, and then you transfer all these forces to the center of mass of the body. And so then the y component goes here and the x component goes there, and then you introduce a torque. So there are a number of steps you have to take. The essential thing is that you're again back to lecture 1, where you say, oh yeah, I'm going to cut bodies, introduce forces, and so you make these free body diagrams. And that's actually not what I want to do, because in lecture 2 we learned this very nice systematic approach, and then the question is, can't we do that also with elements like this? And the answer is, yes, we can. Yes, we can. Okay, our starting point is, of course, for the systematic approach, as always, virtual power. And the virtual power expression as we know it until now, let's start with an unconstrained system. Virtual power equals the applied forces minus the inertia forces times this virtual velocity, and that thing should be 0 for all virtual velocities which fulfill the constraints. And that was the topic of last week. I'm not going to explore that. Now, what we're going to do is we're going to extend our power a little bit, because not only do we have that the applied forces and the mass of the system have virtual power, but we now also have a passive element which can store or release power. So if we add that to the equation, then we're in business. Then we have again our systematic approach. So we have extra virtual power from the spring, in this case, and let's give it a name. I said, well, that's the delta PS. And what is the power of a force which goes into a spring? Well, it has to do, of course, with the spring force, Fs. I call it here Fs, spring force, and then it has to do with the elongation of the spring, right? And since it's power, it's the elongation rate. So that's the power, force times velocity. So this guy we're going to add to this expression, and so we're going to make a new virtual power expression, delta P star, which is then, in some way the sum of the two. I will explain in a second. So we take the original one, times delta x dot I, and then I add, but I use a very strange add sign. I use a minus for adding. I add the virtual power of the spring. Now, why do I use a minus sign? And of course then it's not the real elongation velocity, but the virtual one. This is just a sign convention, right? And if you're not sure about that, read the book. It's also how we add constraints. If I remember well, I even during the lecture I added it with a plus, and in the book I add the constraint with a minus. It just has to do with how do you define your force, or how do you define. So apparently this is force times velocity is apparently for energy which I put into the system, and it is energy which is stored into the spring. Anyway, it's just a sign convention. And then that should be 0, yeah, for all the virtual velocities which fulfill the constraints. That still has to be the case. And we know how to do that from last week. Now, if we look at the equation, it doesn't help us so much, because here we have virtual velocities in terms of the center of mass velocities of the body, x, y, and phi. And here we have a virtual elongation rate of the spring. So we actually have to express this guy into this guy, right? So we have to express our virtual velocities of the elongation. What are they in terms of these guys? And that's actually pretty easy, because we have an expression for our elongation, right? We have an expression for delta L. That is just the current length minus the initial length. And how do we calculate the current length? Well, if I look at the picture, it's just finding out what are the points. So this is point E. Did I give it a name? Oh, I give this a name D, and this is E. So the current length of the spring is apparently, yeah, the x from D minus the x from E squared plus the y from D minus the y from E squared, and then the square root minus L0, right? So given those 2 points, one is the attachment on the body, the other is a fixed point, you can calculate what is the length and what is the elongation. Now, some of these coordinates are a function, of course, of the position and orientation of the body. So where is this point xd? So in this case, xe is a constant, so that is super simple. Xe was 0, and the y of e was L over 2, if I have it right. But then x of d is, how do I calculate that? Then I have to look at the figure. Well, I have to go to the center of mass, and from the center of mass I have to go this distance to point D. And that has to be in a general configuration, right? So let's draw some figure that sort of helps us. This is the general configuration, and here we have this point D, and this is point 1, and this distance, if I'm right, was 2/3 minus 1/2 is 1/6, yeah. So 1/6 times L. And then, of course, we have the general orientation phi 1, and then we have the positions x1 and y1 here. So we can calculate the position of point D, given that we know what the center of mass, the position of body 1 is. So for the x, it's x1 plus L/6 times cosine phi 1, right? And for yd, it's y1 plus L/6 sine phi 1. Or, in a general sense, you could say, oh, this delta L, I can write that apparently as a function of the coordinates and some constants. So just some expression can be with square roots and whatever. Yeah.
Why would you do x1 apart? Because d is always in verlengde from x1.
Point D. So the question is, why do I take x1? Because point D is a part of rigid body 1. So when I know where rigid body 1 is, I can calculate any point from rigid body 1, and also point D. Given the position and orientation of body 1, I can calculate any position. D is a part, so I calculate that as function of body 1. In general, a spring will be between two bodies, and the other attachment point is a function of the other coordinates, and you can make it as complex as you want.
Why don't you need I?
That's the general expression. So in general, when I have K springs, I have K springs, and all the elongation of all these springs are a function of all these coordinates plus some constants. Yes. General case. So yeah, general case. Now we were seeking, remember, we were seeking this delta L dot, right? that is super simple. Forget now for the delta first. So what is the delta L dot? By definition, that's the delta L comma I times x dot I, and then the virtual one is of course nothing else. So this is the Jacobian times this delta x dot I. So here we have again the Jacobian of this expression with respect to coordinates. Here we have finally our virtual velocities on the level which we were seeking. So now we can plug that into our equation here. So we get our delta P star equals then our applied forces minus our inertia forces times the virtual velocities, and then minus, and then all the springs that we have, well, we have one spring here, times, and now I'm taking this expression, I substitute that, so that's delta L comma I, the Jacobian, times the delta xi. That should be 0, for all these virtual velocities which fulfill the constraints. So now we have found a systematic way of putting that stuff in. Now this is sort of ugly, Fs and delta Ls, so let's go to a bit more a general approach. Let's say that we how did I call them? Cs. Okay. The delta Ls, I'm gonna just call them constraints of the springs, which are a function of xi. Those are, I could say they are, or just a general way of writing. Then if I want to then incorporate these here, then again I need that Jacobian, but I have S number of springs, of course, S springs, or passive elements even. And then we get this delta P star equals, this is identical, x double j minus, and then Fs, as many springs as we have, times Cs comma I delta x dot I. And again, for all blah 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 which fulfill the constraints. I'm going to write that. Now what we see here is that now everything is under the same variation. So if we then write down our equations of motion, and we add the all constraints, and what did I use for constraints? Ck x of I is 0. Mind you, I use a different index here. These are not 0, these are just expressions of elongations of springs. These are constraints which have to be 0. Then in the same manner as last week, I can add them to the equation, and then it holds for all virtual velocities. And then finally the equations I get, of course, is, and let's keep the order, mij x double dot j. Then first I take our spring part, minus Fs Cs comma I. And then of course we get our part from the genuine constraints here. That was, how do we call that? Lambda, right? For the multipliers, lambda k Ck comma I is 0. So these are our equations of motion. EOM. Now, what is known and what is unknown? So let's do the underscore for the unknown quantities, right? Well, the applied force we know, right? The mass matrix we know. The accelerations, no clue, so we don't know. Spring forces, known or unknown? Unknown? Can I see hands for those who say unknown? Yeah, can I see hands for those who say known? Oh, it's a 50-50. Well, the spring force is a known quantity because, bear with me, they are a function of the spring constant times the length. Well, if I know the configuration, I can calculate what is the length of the spring. So I can calculate what is the spring force. So that is a given quantity. I know what the force is. Yeah? Jacobian, I know what the thing is. Yeah? Just in that configuration. Lagrange multipliers, no, unknown. Eh? And then this Jacobian we know. So now when we reorder stuff with known and unknowns, how do we do that? So we get Mij here, and then we get this Cky, and of course the matrix is bigger, we have to add the constraints, but that's not the point now. X double dot j, these are also unknowns, and then on the right hand side we see our forces, Fi, plus this term of course, and with a strange plus sign, Cs, I, Fs. And here clearly we see that these are now the spring forces. Spring forces. And as you can see, the spring forces which are transferred by the Jacobian to the forces at the center of mass. So I will repeat. Here we see the spring forces at the center of mass forces, and that's the spring forces, and this Cs, I, that makes this transformation from spring force to force at the center of mass. So all the stuff which I explained in the beginning, like cut the body, introduce the force, two components, X and Y, and put it, that's all done automagically by CSI. So CSI is some automagic thing. If we would draw a picture of that, then here we have our body, here we have some spring, where, well, let's say there is a spring force Fs in some configuration, and then what does CSI do? Well, it makes this out of it. We have a body here, and it makes nicely a component here, Fx, a component here, Fy, and a component here, M, of the spring. And that is what our CSI does. Well, how does it do it? Well, let's focus again on what was this CSI. So the CSI in our case was the delta L differentiated with respect to the coordinates, which in our case was for this one body with this only these coordinates. It was the delta L differentiated with x1, the delta L differentiated with respect to y1, and then the delta L differentiated with respect to phi1. Three numbers, that Jacobian. And in our case, if we just go through the motion of doing that calculation, it turns out that this Jacobian becomes 4 over 5 minus 3 over 5, and here minus 1 over 10 L times L. Well, not times L, 10 times L. Yeah. Just numbers, right? But what does it mean? Well, if we interpret this, we say, oh yeah, this CSI transforms this force to the forces at the center. So apparently the system is like this. And remember, there is a minus sign here. So we have to put a minus here. So I put a minus here and here a minus, so I won't forget. So this is then apparently equal to Fx, Fy, and M1. So let's draw that in the figure. So the horizontal force at the center of mass due to that spring here, right? This spring, apparently here. So these are totally equivalent, right? So that's minus. So 4. So that's a bigger one. So 4 over 5. Then in the y direction, apparently 3 over 5. and the torque we get is minus times minus is plus, and plus is like this. So we get a torque of Fs, I should write, of course, times Fs. And this is then 1 over 10 Fs times L. Yeah, question?
Yeah, why is in the picture on the right, X and the Y, why are they switched? Like the F.
Oh yeah, because I made a stupid mistake. Thank you very much.
Okay.
Yeah. The reason is always that my brain is faster than my hand. Yeah. If you make errors in writing, your brain is faster than your hand. And that's actually all I have to say about adding active and passive and active elements. Of course, I haven't talked about an active element yet, but an active element is treated in completely the same way. And let's for a second take a look. What is an active element? For instance, you have a motor, right? On the motor, you put some current, some voltage. Now, mechanically, remember we have a rotation here, but that is the rotation of the axle. But we also have a rotation of the housing. I mean, these two have a relative rotation. And the whole thing, what is important is the relative rotation of the thing, not the absolute rotation. So you have a housing rotation, phi 1, and you have an axle rotation, phi 2. And actually the deformation of the thing, like elongation of the spring, what is the deformation that's the change in the rotation. So the delta phi is the thing we have to look at. Then it makes sense. And if we think of a motor, it's not the angle, but it's the angular speed, of course. So the delta phi dot is then this phi dot 2 minus this phi dot 1, and that is what we recognize as, oh yeah, that's the angular speed of the motor, omega. And what is the spring law of the motor? Well, the spring law of the motor is, of course, we have this torque, and this is the reaction torque, all Newton, torque at the rotor, torque at the stator. And then what is the spring law of the thing? Well, we have an angular speed, and then we have a torque, and depending on what type of motor we have, what type of motor do you want? Alternating current or direct? Direct? Okay, let's take a direct current. Then the lines go like this. And if you increase the voltage on the motor here, so it should be direct, sorry. If you increase the voltage, then you have one of these lines. Remember, if you stall the thing, then you have a high torque, but don't do it for too long because becoming smelly and the thing will burn. And if you just release everything, then you hear a very high speed here, and there's no torque, almost no torque, and everything in between. And if you want to have more torque, you put more voltage until the thing starts smelling. That's how it goes. By the way, the same, I want to do also an alternating one, so an asynchronous one, async alternating. That works a bit different. Then you have functions like this, because it operates in this area, almost asynchronous, almost synchronous with this speed. That's one of the advantages of such a alternating current motor, that you have a whole range of torques for approximately the same speed. And don't use it here or here because it will start smelling again. But anyway, the bottom line is here again, also for these motors, these active elements, it is some function of the coordinates. And again, you can find some law for these forces depending on what the state is. The law is in this case not with the spring, it's on the length. With the motor, it's on the change in length. But anyway, you can put it in the same, exactly in the same rule of this whole framework. Okay, let's take a break, and after the break we're going to talk about impacts. Even kijken hoor. OBS. Stop record.